Okay, hi everyone. So, video 2 on proof. This one's a lot more involved than what we were doing before, the counterexample, exhaustion, or deduction. This is proof by contradiction. This is a second year topic, really. Um, and how it works is there's going to be a statement given to you. So it says here, for example, prove by contradiction that if n squared is even, then n must be even. Contradiction always works the same way. What you do is you're going to assume the opposite is true and then show that it's impossible. So therefore, the original statement must be correct, you see? So, assumption, okay? Assumption, it says, prove by contradiction that if n squared is even, then n must be even. So we're going to assume the opposite is true. So we're going to assume if n squared is even, then n must be odd. Okay? So how do we write an odd number? So assume then that n is odd, so we'll write that as n equals 2k plus 1. That's the way to say an odd number, isn't it? Because 2k, if it's just 2k, then it's divisible by 2. If it's 2k plus 1, any even number plus 1 will make an odd number. So therefore, n squared will give 2k plus 1 squared. That's 4k squared plus 4k plus 1. I'll take out the factor of 2. Right? Because remember what we're trying to say. We're saying if n squared is even, we should end up with a number which is a multiple of 2. But we don't. We end up with a number multiple of 2, add 1. So this is a contradiction. This is a contradiction. N squared must be even. That's what it said at the top. So therefore, n cannot be odd. You see? N must be even. So you always start with an assumption. You then state the opposite of what they're saying is happening. That's your contradiction. And you'll see that it's impossible. And then you close with a final statement. Let's try that again. So it says, prove by contradiction that if n squared is a multiple of 3, n is a multiple of 3. Right, okay. A little bit more difficult this time. So we start off with an assumption. Again. So we're saying that if n squared is a multiple of 3, then by contradiction we pick the opposite of that. So then n is not a multiple of 3. Okay? Now the reason I chose this question was, well, how do you express something which is not a multiple of 3? What does that mean? Well, we're going to let n then equal, obviously 3k is a multiple of 3, isn't it? But 3k plus 1 is not a multiple of 3. So 9 plus 1 is 10, not a multiple of 3. 12 plus 1 is 13, that's not a multiple of 3. And also 3k plus 2 is not a multiple of 3, is it? So 9 plus 2 is 11, that's not a multiple of 3. 12 plus 2 is 14, that's not a multiple but plus 3. So can you see if we did or let n equal 3k plus 3, that is a multiple of 3 because I can take out a factor of 3, you see? So 3k plus 1 and 3k plus 2 are really the only numbers that we can pick where k is an integer. So I should have done that in the previous one. That means, remember, k is an element of the integer set. So they're whole numbers, yeah? So these are the two numbers that we have to work with then. So if I put in n squared, so n squared would equal 3k plus 1 squared for the first one. So that's 9k squared plus 6k plus 1. Take out the factor of 3, just like we did before. And we can see not a multiple of 3. Okay? Because we've got that plus 1. Likewise, if we have n squared 3k plus 2 squared, that's 9k squared plus 6k plus 4. And again, take out your 3. And we've got 4 left over, which is not a multiple of 3. so not a multiple of 3. This is a contradiction. So contradiction. And this is exactly what you would write, by the way. So contradiction, exclamation mark. Hence, if n squared is a multiple of 3, then, let's put this up here, then n must be a multiple of 3. Because it doesn't work for any other number. Do you see? This accounts for every other number possible. Part B, a little bit more in part B, remember that fact it says hence suggests I should use my previous information. Okay, so I'm going to prove that by contradiction that root 3 is an irrational number, and this is a common thing, prove that something is an irrational number. So it's important to know what an irrational number means. An irrational number means that you cannot write it as a fraction of one integer over another. So I can't write root 3 as a fraction. You know, it's not a half, it's not 3 over 4. It's not, I can't do it because there's an infinite number of decimal places if you put that in your calculator. If there's an infinite number of decimal places without repeat, because remember a third is an infinite number of decimal places, isn't it? It's 3, it goes on forever. But an irrational number means there's no repeat of decimal places, there's no pattern. It's completely what seems to be random, okay? So, for part B, again, assume by contradiction that this is an irrational number. Let's do that again. So we'll do the assumption. So we're going to assume then the opposite. We're going to assume root 3 is rational. So assumption, assume root 3 is rational. And if it is rational, then I can write it as I have done here, which is a over b, where a and b are integers, and a over b is in its simplest form. Okay, so it's broken down to its simplest amount. Like 2 over 4 is obviously the same as a half. So it must break down. So it can't lower down any more than that. It's a rational number, right? So how do we prove this by contradiction? Well, if we times up, okay, and if we square both sides, so root 3 squared is 3, b squared is a squared, you see? So can you see, because a squared is 3 times something, right? A squared must be a multiple of 3 then. And from part A, we said that if n squared is a multiple of 3, then n is a multiple of 3. So therefore, a must be a multiple of 3. Do you see? That proof has led us to say that therefore a we could express as 3k, where k is an integer again. Okay? So if a is 3k, then if we go back to this, we get 3b squared is a squared, but a is 3k squared. So 3b squared is 3k all squared, sorry. What is going on? Okay, let's try that one more. Squared, so that's k squared, right? If I divide both sides by 3, because now I'm investigating b, so b squared is 3k squared. Again, b squared is a multiple of 3. Right? Of 3. And we just said it again from above, that if b squared is a multiple of 3, then b must be a multiple of 3. And again, we can say then that b can be, I don't know, call it something else, 3z. Okay? Now this is a contradiction. The reason why it's a contradiction is because we said that root 3 was a over b, and a, we said, is a multiple of 3, and b is a multiple of 3. So that means this 3 would cancel down. But it can't, because we said at the start that a over b must be in its simplest form. So since a over b must be simplest form, root 3 cannot be rational. Cannot be rational, yeah. Okay, so root 3 must be an irrational number because this can't break down any further because a and b was in its simplest form. Okay, last one. Last one. So this one, prove by contradiction that there are infinitely many prime numbers. And you probably know that there are an infinite number of prime numbers, but how do you prove that? Well, again, our assumption, we assume the opposite. Okay, so assume there are an infinite, and there are a finite, sorry, number of prime numbers. Right, number of primes. And if we can list them, right? So let's say we've got the first prime number, the second prime number, because if there's a finite number of primes, then we could know them all, couldn't we? All the way up to the probability of n, and sorry, p of n, and p of n is the last prime number, right? So imagine if we produce a number. So if we imagine that we have a number n, where we times them all together. So p1 times p2 times p3 times p4, all the way up times pn. Do you see? Right, so we're going to take that number, and then we're going to add 1 to it. So imagine there exists a number where we times all the prime numbers together and we add 1. Right? If we add 1 to it, there are no factors here, are there? I can't take out a factor because all the factors, I've used up all the prime numbers. So if I add 1 to this number, there's no factor that I can take out, right? So there are no factors here other than 1, right? Because I can divide it all by 1, or n, the number itself, which is the definition of a prime number, which is a contradiction. Contradiction. Because if it's 1 divisible by 1 and n only, then n must be prime, as n must be prime. So that means we've found a new prime number. So therefore, cannot be a finite number of primes. Number of primes. You see? It can't be a finite amount because we just found a new one, right? That whole number plus 1 cannot be divisible, cannot be divided by any other prime number. Okay, so lots of examples there, proof by contradiction.